In this series of videos, I'm going to look at the June 2013 F322 paper. So question 1 is about crude oil and the petrochemical industry. So we're told that crude oil is a mixture of hydrocarbons, many hydrocarbons, remember that's C and H only. It's processed by the petroleum industry to make fuels and petrochemicals. The straight chain alkane, so again, I've just written up there CnH2n plus 2. So these are just little triggers as you're reading through the question of things they might ask you. Molecule A has 10 carbon atoms and it's straight chained. Molecular formula of A must be C10, H2n plus 2, so H22. B is a branched chain isomer of A. Draw the skeletal formula for a possible structure of B. There's lots of possible answers here. I've just gone for the easiest one. I've turned it into a continuous chain of 9 with the branch on the second carbon. So that would be 2-methyl nonane. Branched chain isomer B has a lower boiling point than the straight chain alkane A. Explain why. So that's all about surface contact due to branching. So branching reduces the surface contact between the molecules. They can't get as close together, can't pack as close together. And so the van der Waals forces between the branched chains are weaker. And so therefore less energy will be needed to break the intermolecular forces. Remember, you're not breaking bonds, you're breaking intermolecular forces between the molecules. Part B, a chemist heats a pure sample of C15H32. So just check CnH2n plus 2, so that's an alkane. The reaction cracking occurs. Remember, cracking makes an alkene and an alkane. Construct an equation to show the cracking of C15H32. Again, lots of possible answers, and I've gone for this one. So there's my alkene, C10H20, and there's therefore that my alkane must be the difference. So I've gone for C10, so that must be C5 to get the 15. There's H20, so that must be 12 to get the 32. Lots of possible answers. Why? Because the carbon chain, or the carbon-carbon bonds in the hydrocarbon, can be cracked in lots of different places. The petroleum industry, so that's all about the manufacture, the processing of crude oil industry, processes straight chain alkanes into cyclic hydrocarbons. For example, octane can be processed into a cyclic hydrocarbon and hydrogen, suggest a structure. Again, lots of possible answers here. I've got some extra ones down at the bottom there. I've just gone for the obvious one. So if we've got 8 carbons in octane, therefore the simplest cyclic answer would be cyclooctane. So it would look like that. I'll just flick down to the possible answers. You could go for something a bit more complicated if you wanted to impress the examiner. You wouldn't get any more marks, I'm afraid. So you go for a cyclic hexagon. So we've got cyclohexane, and then you'd need 2 branches on there. So that would give you 8 carbons. You could go for a pentagon with 3 branches on. You could even go for a pentagon with a single branch and then an ethyl branch. So lots of possible answers for that one. And then classic question, why does the petroleum industry even bother to do this? And it's because the cyclic hydrocarbons burn more efficiently. They increase the RON value, that stands for research octane number if you're interested. It increases the RON value of fuels and therefore they burn more efficiently.